Okay.
Okay.
Hi, everybody. Thank you for joining us today. My name is Aisha, and I am one of your Solid State Circuit Society staff members. The topic of today's webinar is Open Source IC Design, Viewpoints from Academic and Industry, presented by Matthew Gutos and Christoph Sandner. Today's webinar will be a little over an hour, and we'll hold a Q&A session in the middle and the end of the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I'll put a link in the chat box with instructions on how to obtain the certificate, and the webinar video and slides will be posted on the SSCS YouTube channel after the webinar. Please use the Q&A section on your dashboard to ask any questions. I now invite SSCS Webinars for Young Excellence Committee member Sean to introduce our speakers and give a few welcoming remarks.
Yeah, thank you, Aisha, for your introduction. Hello and welcome to this webinar. I'm Sean Zhou, a staff engineer at Qualcomm. I'm the moderator of this webinar. Before kick off the panel discussion, I would like to spend a few minutes introducing ourselves. So as a young professionals and students, you make up to 30% of our overall membership, and you are the future of the IEEE SSCS. As the SSCS Young Professional Committee, we strive to address the different needs and interests of our younger members with initiatives like this webinar today. So our IEEE Young Professional SSCS and students also have a bunch of benefits, such as we have the access to the resource centers, distinguished lectures, and we provide some student travel grants, pre-doctoral achievement awards, and circuit design contests. We also provide up to 1,500 young leadership volunteer travel awards for SSCS conferences, and you will have the chance to become a young professional leader in your local SSCS section. We also provide SSCS Young Professional Networking events at all SSCS-sponsored conferences such as ISCC, CICC, VLSI, ESSCRC, and ASSCC. We also provide a new mentoring program called Chronos, which connects you with the leading SSCS mentors at your pace and time. And if you are interested, please sign up through the SSCS website. Our next in-person mentoring event happens at ISCC at February 20th in San Francisco. Since 2020, we have hosted webinars for Young Excellence, which is a quarterly webinar series dedicated to young professional members. Currently, there are 7 committee members to operate this webinar. We focus on technical tutorials and developments. These webinars are available at SSCS at SSCS YouTube channel. So let's get started with today's topic. It is the open source IC design viewpoints from academic and industry. I would like to briefly introduce our 2 speakers. Our first speaker, Mr. Christoph Sandler, is a senior principal engineer at Infineon Technologies. He received the master's degree in electrical engineering from the Technical University of Graz, Austria, in 1995. Since graduation, he has been with the Microelectronics Development Center of Siemens AG, now Infineon Technologies, in Villach, Austria. His main interest is in architectures and design of analog and mixed signal circuits and the related analog design automation. Our second speaker is Professor Matthew Gutos, who is a professor in computer science and engineering at the University of California, Santa Cruz. He received his BSE in computer engineering and MSE and PhD in electrical engineering, all from the University of Michigan. His research interests are in low power computing and electronic computer-aided design, including new circuits, architectures, algorithms, and software to address challenges in modern design flows. So I will let the 2 speakers take over the webinars for now. And Professor Matthew Gutos, can you start with your?
Sure, let me share my screen here. All right, does that look good? Can everyone see my
looks
screen?
good to me.
Okay, so thanks for the introduction, Sean. And as you mentioned, I'm Matt Goodhouse. I'm at UC Santa Cruz. I'm going to give a talk on open source IC design, kind of my opinions from academia. If you notice, I'm at the UC Santa Cruz VLSI Design Automation Lab. If you notice in this, the S is a little funny in our logo. That's a banana slug. And that is actually our school mascot. You can see a picture of one that my wife took on the left. You can see the mascot on the right. And there's a famous t-shirt from Pulp Fiction, the movie, in the middle. And I always answer, yes, they are real. No, you can't eat them. And we have it as our mascot because there's, quote, no known predators of the slug. So just a funny tidbit to open up. So when I started thinking about this, I was trying to figure out how I wanted to approach this talk, and I decided that I need to step back and look at the question of why has open source succeeded in the past first, and first of all, what does it mean to succeed, for example, in industry, and then we'll talk about what does it mean to succeed in academia, and those are different things, and they're going to have different metrics for success. So in industry, you're going to have three main people that think about success: a business person. They're going to mostly think about money. Can you make money with something? Can you save money with something? On the other side of that, you're going to have an engineer. They're mostly concerned about functionality. Can I reduce my work by using something that's already existing? And is that thing stable and easy to maintain and reliable? I don't want to have to replace it over and over again or fix bugs. And then the counterpoint to both those, the non-industry person, is the user. And a user doesn't care about any of that. They want a final product. They want that final product to have new features, to perform well, and so on. They don't care what goes on inside. So what this boils down to is an engineer and a business person really don't want to reinvent the wheel and make things that already exist, right? You can't make a wheel twice as round when it's already round. So that's the motivation for industry. On the other side, what does academia define success in open source? And I'll start this by saying one of the most successful open source things in history are libraries. It's access to information that you can easily get. In academia, you have educators and students. Educators want accessibility, and so do students. They want easy access to information. Educators want it so that they can demonstrate new ideas and concepts easily and in realistic ways. But they also want this to be easy to use so that they can provide it to their students in a way without a lot of effort. You don't want to have to worry about licenses and NDAs, legal stuff. And that's something that's beneficial for educators. Students, on the other hand, want to learn in a variety of ways. They want to have hands-on learning in labs with real kind of production-ready tools and designs. And they want this to be representative of real stuff. They don't like toy examples. If you have a little example problem at the end of a chapter in a VLSI design book, that's not worth as much as a real circuit that you can simulate and you can even fabricate. So they want representation of the real world. Now, what are some examples of success in the past? Well, in industry, there's been a large number of them. Most of them are in the software area so far and not in the IC design area. But we can look at these a little bit and see some patterns. We all know Linux. That's probably the greatest open source success story of the last several decades. It's in products from phones to embedded devices and the biggest servers in the world. Another one that you don't think about much is the GNU compiler collection. People used to charge money for compilers that would take C code or C++ code or whatever code and translate it into machine language. Used to pay license fees. It was expensive. Now there's an open source version that's very good that does this. And there's several of them actually, and it's high quality results. Now, also on the web end, you see things like Apache, the web server, MySQL, the database behind a lot of web servers. More recently, you see TensorFlow for machine learning. Now, Now, on the academic side, most of the examples of success so far have been just in information dissemination. I cite, I think the best example that everyone uses is Wikipedia. We used to have encyclopedia salesmen that would go door to door selling information of encyclopedias that you could buy. Now we have everything available at our fingertips for free, and it's open. Similarly, Project Gutenberg, I might have spelled that wrong, I don't know. They provide access to out of copyright books for free. So classic books, you can just go and download the thing in any different format. More recently, we have YouTube and MOOCs, which provide a lot of lecture material and things that are a lot of students are relying on for additional tutorial and so on. Now, what all these have in common? Well, I'm going to say, in order for open source to succeed, it has to be a commodity or off-the-shelf component. And what is the definition of a commodity component? Well, I took a definition from a dictionary here, and I kind of put red squares around some of the important points. It has to be a mass-produced or unspecialized product. It has to provide something useful or valued. And then the final one there, it's a good or service whose wide availability typically leads to smaller profit margins and diminishes the importance of factors such as brand name other than price. In the past, we think of commodity as wheat, corn, basic building ingredients for food and other products. We can think of things in the IC design and open source EDA area as commodity products too. Most of these things we can classify as commodities. If you think of Linux, there were a lot of different operating systems, but in the end, an operating system just runs stuff and it is really kind of unspecialized. You don't want to think about it. A compiler, it does one function. As long as it gets the right result with reasonable performance, you don't care. It's kind of unspecialized. Web server stuff, it just has to deliver information. TensorFlow is a little bit of an exception here on why it succeeded. So I'll put an asterisk there and happy to talk about it later. But then on academic side, a lecture about intro VLSI is the same, pretty much the same as another lecture about intro VLSI. And an article about banana slugs is going to be the same as another article about banana slugs. There's not going to be a lot of difference in the material. So these are pretty much all commodity products. So where does this bring my predictions for open source design? Well, I think that we have to go back to this idea of specialized versus unspecialized and open source. And open source digital IP design, I think, is going to flourish. And I think if we look back in a decade, it's going to seem crazy that people are licensing unspecialized cores. And what do I mean by unspecialized? Things like a CPU core. It executes instructions. We don't care much about performance so much anymore. We've kind of hit that limit. And so just if it works, it works. Encryption cores, things like that. These just perform a function and it adds value, but it is in general not specialized. For the same reason, though, I think things like analog IP are not going to flourish as well because they actually, by definition, have to be specialized for a particular technology node. You can't say, here's an ADC in one technology, it automatically works in another technology. It has to be specialized. In addition, in the digital domain, we're going to see that the secret sauce of a lot of products is still going to be specialized parts. Think of the core in your iPhone. It has all these accelerators. One of those accelerators is an accelerator to just do the depth of focus calculation for the camera. That is incredibly specialized, particularly for the camera setup in an iPhone, and it's not a general thing that everyone would want to use. And so they're not going to open source that, and I don't think that there would be a market for something open source like that yet. And I'll put a big yet there. Open source EDA is kind of similar. It's going to find success in a couple markets. We've already seen that it has a lot of good success in simulation, both digital and analog SPICE simulation. There's great simulators out there, and I know a number of companies that are using these simulators for primary development. Layout editors are another thing. As long as you can input polygons, input shapes, and you get out the standard formats that are correct, they're a commodity component. it doesn't really matter much how they work. We're going to see similar success in FPGAs, and this isn't because FPGAs are not specialized. There are different flavors of FPGAs that are all different, but the concept of an FPGA is kind of unspecialized. You have reprogrammable LUTs, you have reprogrammable switches. That idea is general and unspecialized in itself. And so I think we're going to see a lot more success of open source EDA tools in the FPGA market. We're going to see mixed success in ASICs. It depends, again, on this technology question and the size of the design. So it's going to possibly succeed in older nodes, which are not, you don't have to worry about details of, device models and physics effects as much. And it's also not going to be used in a lot of complex designs, because then you have to start worrying about performance and scale of the tools. And I'll put a big asterisk there, because it's very much possible that we see a bootstrap effect, that open source actually helps create more complex designs, because you're, again, not reinventing the wheel. So, I see these kind of conflicting things. It's necessary for something to be a commodity for it to succeed in the open source market. That can be different for academia, because it's more of the information aspect rather than the product aspect. And I hope that my personal preferences, I hope that I see a lot of these things, and we're going to see a trend toward this over time. So that's my presentation.
All right, thank you for Professor Matthew for his sharing. Now let's move to our next speaker, who's Matthew. Can you share your screen?
Oh, Christoph.
Oh, Christoph. Oh,
Sure.
sorry.
All right. Size is okay?
Looks good.
Okay. So yeah, thanks Matthew for opening the stage. So now I'm focusing more on the industry perspective, but I'm gonna start with an aspect that is strongly related to academia as well, which is workforce and education. So the shortage of skilled electrical engineers resources today is a real issue for industry. So to find new people is a clear problem. One aspect is that computer science seems to be more attractive, and electrical engineering is a quite complex topic to learn. There's no abstraction. You need many years before you can really start getting hands-on experience on chip design. So that's one big topic we have to face for the coming years. And the second topic or problem statement I have here is for industry, R&D efficiency and time to market are crucial things that we have to improve, because industry competes on maximizing the EBIT, the earnings. But on the other hand, the complexity and effort of chip development increases by a factor of 2 or even more for every technology node that comes. People or companies that have to switch from bulk nodes, CMOS nodes to FinFET nodes have to make a big step in productivity. And yeah, last not least, analog was mentioned already. There are still a lot of manual design steps and lack of automation. Digital is a bit in a better shape here. So related to this aspect, I found this nice diagram about popularity of the green curve, which is computer science, which was rising over the last decades, comparing it to electrical engineering, which was on a more or less continuous decrease. So we have to really ask ourselves, how can we bring up the popularity of electric engineering again? Or is this a dying species? But on the other hand, we all need analog engineers and digital engineers and so on to build our hardware. So I'm rather of the opinion that we should not wait until we die out, but we should act and do something against it. So what can we do? I believe academia and industry need to join forces here to solve this problem. So it cannot be solved only by academia to bring back the number of students that we need. And open source could now be one of the enablers to help here. And I see here these relevant pillars. So first, I mean, I'm from industry, so open source, if I go this way, it has to provide value in one or the other way. It can be financial or savings. Education is an important pillar. Open source PDKs, so process design kits, are coming more and more. Open source IP, so building blocks that can be shared easily, and last not least, automation, where open source also could play a big role. Let's have a look on open source success stories, and Matthew already mentioned a few. I have two more to show. One is RISC-V, which offers a free and open source instruction set architecture, and around this instruction set, a big ecosystem was growing, and the market size 21 was about $440 million US, and a huge growth rate over the next years still seen. And the interesting thing here, also, the initial thing was open source. It still is an ecosystem where both open and proprietary solutions can be offered. So it is possible to also earn money with going open source. Big success. Another big success is WordPress. So today, almost half of all the websites worldwide are powered by WordPress. Why is that? Because it enables a variety of plugins. It's also a huge ecosystem behind, where people found ways to make money also out of it. It has a very low entry hurdle. Everyone can design and maintain a small website. And their mission is democratize publishing. And a few years back, Boris Moorman, if I recall correctly, brought up this phrase, why not democratizing also IC design? And this is one example where this is currently followed, which is the solid state circuits PICO program, where basically the vision is that chips can be designed through a web browser by anyone, and this will help to accelerate the construction of the required ecosystem. So you can have a look to their website. They offered free shuttle runs using open source tools and open source PDKs. So this is a really nice initiative working on solving this initial problem that I mentioned. Another interesting idea was brought up by Google on SCIRC 22. They showed here this fact that today, if you want to do chip design, you only do this during your master's and your PhD. Why is that? Because today it takes a lot of money and a lot of learning to get hands-on experience. But in future, if you have open source tools and open source PDKs and simple shuttle runs, the cost can go much down, and it would enable that you can even do your first tape out in middle school. So for me, this is a really nice opportunity that is shown here. We are not yet there, but it's really going in this direction. What do we need? PDKs. There are open source PDKs coming up more and more, 130 nanometer, 180 nanometers. So not the most advanced nodes, of course. IHB from Germany stepping in with an BiCMOS, where you can already do even RF design. And yeah, a lot is going on here. What else do we need? Design systems. We see a growing number of open source design systems. A few are mentioned here. And around these design systems, also a growing ecosystem is already building up. A few companies mentioned here, mainly startups and small companies who try to grow this ecosystem here. How about IP design? In digital, there's a lot available. In analog or mixed signal, there is not so much. And this is a very recent paper that was published by Harald Bretl from University in Linz, Austria. They did a self-clocked 12-bit ADC, SAR ADC, using an open source PDK, and the entire tool chain was created with open source software and tools. So really interesting example to see, because sometimes you hear people saying, yeah, that's not possible, and the open source tools are not as good as the commercial tools. Of course, this is true still today. A lot of open source tools, you cannot do similar things like with commercial tools, but you can do design and create a GDS and do a tape out of a relatively complex ADC. Topic of automation. This is something I'm an analog guy, so I'm very interested in this one. And yeah, it's kind of a holy grail to do analog circuit synthesis. And today we don't have a good solution here. There's a lot of research going on. Different institutions, universities put effort here. But what we miss here is a common condensation nucleus. And also here, I believe it would help a lot to join forces and not have a lot of different solutions that, yeah, overall don't bring so much benefit. So what opportunities do I see with going open source? Tool chain I mentioned already. Would be really nice to have a common open source framework for analog circuit synthesis. We don't have this today. It would enable a various tool plugins. You can go applying AI in the end. It allows fast creation of analog IP for different specs. It would create a new market for analog generator IPs. That's, of course, something not easy to achieve, but I believe this is doable. And then, of course, small companies could offer value to the open source ecosystem. PDKs offer a low entry cost to design your own chip, and open source, last not least, will ease, of course, collaborations and lower the entry barrier. So for teaching, it's good enough already. That's what I see. You have no licensing issues, no NDAs. This also helps us as industry to do university cooperations, and yeah, to get also funding money for research projects. One precondition today more and more is that results are published open source. And it's coming to my enablers: people, money, and collaboration. So the open source community is often fueled by individuals, and then companies, especially big companies, only step in if they really see value in going there. You need money. Funding helps here a lot to do some initial seed funding here. And collaboration is a big enabler, and that's one of the key things when you go open source. And there are foundations out there which help you in this collaboration. Also to provide a common ground if you want to get something standardized, APIs, for example, interfaces between these tools. And what I still see is that we need a mindset change in hardware industry to see open source as an opportunity and not as a threat. What did we do at Infineon? 22, we founded a very small team with some partners to work together. We did a boot camp together with Silicon Austria Labs. This was in the lead at that time. And last year we organized a summer school at Infineon Austria, where we invited 50 students to learn about analog design, also encourage them to look into this idea of analog circuit generators. Yeah, so my last slide, 2024, I'm really curious and looking forward. We will continue step by step. And yeah, that's all from my side, and looking forward to your questions.
All right, thank you, Christoph and Matthew, for your presentations. So now let's go through the panel questions. So I will start with the questions. So first one is I heard that both of you mentioned that this open source, either it's open source projects or open source tool, EDA, PDKs, they provide a lot of values, benefits for education, for individuals, for to innovate, to collaborate. But you also mentioned that in order to develop these things, companies, they must see value, right? So I was wondering that how can those companies see the values here and motivate them to provide more and more open source tools and PDKs? Like you mentioned, the Global Foundries has already opened, TSMC opened some old technology node. How do they see value? What the value they see, and how do we motivate them to open more like this?
Mhm. So there are different aspects to your question. So for the companies that offer open source PDKs, I would assume the value is that they can get new customers. So today it's really tricky, or it's not so easy to design a chip and tape it out in low volume. With high volume, you can approach the big companies like Infineon or any others. But if you just want to design a small chip, not so complex, and low volume, and then put it into your product, then this could be a very nice offer or opportunity for you as a company. And on the other hand, for the PDK provider, for the foundry, to create here new business with these customers. That's one aspect here I see.
Yeah, thank you. So Matthew, do you have any point for
Yeah,
that?
I think it goes back to kind of what I was saying in my presentation. I think the differentiator is the end product. And I think a lot of companies have to focus on their goal is to make a unique product and not worry about the components of the product. And then, from a business perspective, you can reduce cost by using open source stuff. And they have to kind of trust that it's not giving leverage to competitors to have the same CPU when their contribution is the stuff around the CPU and the environment. So I think there's kind of a mindset change that Christoph mentioned in electrical engineers and designs, that you have to have a little bit of trust in the open source concept. And that's why I pointed out a lot of examples in the software realm where we've seen huge successes from companies, Google, and all these companies that rely heavily on open source stuff. And they rely on the community to kind of provide updates and a lot of the maintenance and things like that. And they focus on their contribution. And so it scales much better when you do that. And so I think that's the thing that a lot of the chip product companies need to do. Now, what does this mean for like a company that sells just a core? I don't know. They're going to want to guard that core and not open source it, and it's going to be a challenge to convince them otherwise. I think those businesses are going to eventually have to pivot somehow. Mm-hmm. And I don't know what that means. Does it mean, like you mentioned, providing an open API to their system, or some other mechanism of being a little more transparent so that it can be flexible? It's going to change how some of the business models work, I think.
Okay, yeah, thank you for your inputs. My another question is, like you mentioned a lot of benefits, and are there any challenges or limitations associated with using these open source tools for the IC design? And how do you think these challenges will be addressed?
Maybe I'll go first. I've taught classes, for example, with both open source and proprietary tools. Especially with EDA tools and libraries and stuff, you have bugs. They're low volume compared to a lot of other products, right? You don't have 1 billion Windows users. You have 10,000 users of a synthesis tool at the most. So there's lots of bugs. So I think dealing with bugs is one issue. And here's a question where open source doesn't necessarily make it easier. If you license a tool from industry, they give you support. Open source, you don't have support, but you can go and fix it yourself. So I guess the question is, what do you rely on? From academia, they actually provide little support in the tools because they give us very cheap licenses. Industry, you get quite a bit of support because you're paying millions of dollars for your EDA tools. So from that perspective, I feel like open source is very good for academics because you can easily figure out the problems and fix them and so on. I think this does open up an opportunity for other services. We've seen this with Linux and some of these other things where you can have consulting services to provide support. And there might be a number of open source kind of support companies coming out that will help you with the open source tools. We're seeing this already with a number of kind of smaller chip design companies that they'll help you use open source tools to design a chip, and they'll take some of that burden of finding bugs and getting the tools to work properly. So I think it's opening up a new market there.
Yeah, I totally agree here. So for industry, if we design a chip internally, we really have to rely on high quality tools. We have no time to bother around a lot with bugs and so on. And you get the support from the EDA vendors. And if we go open source, using open source tools, the situation is very different. It's the maintenance, the support is you depend on the open source community. So yeah, you will need some trust, I guess, if you really go this way. And for some tools that are very specific, I believe that are differentiating, like I don't know, a specific noise analysis tool, this will definitely stay much longer proprietary than like Matthew mentioned, the commodity stuff. Here's much more potential that this will be adopted earlier by using open source tools and plugins. And also on the PDK side, yeah, if you get an open source PDK, this might be buggy. You cannot fully trust the model, and you have to cope with this. And yeah, for academia, this is, I guess, not such a big trouble, but for industry, you have to guarantee the specs of what you do. And I also see the opportunity, like Matthew mentioned, that then other companies might step in and provide the quality that is still lacking what is out there in open source, and find an opportunity here. But this, of course, will take quite some time until this will come.
Maybe I can
just at the beginning right now.
Maybe I can augment my answer a little too. I think if we look back in history, a lot of chip design companies used to design their own EDA tools. IBM designed all its own tools. Motorola did a lot of its own tools. There's an economic argument. Everything in chip design is economics, right? How much does it cost? How much do you make? If the tool prices get, so much, it makes more sense for a company to bring in developers and modify open source and to fix the bugs. So the question is there the expertise of people to do that? And I think this is something that open source might be able to have, where if we educate enough students with open source, they can go to a company and say, hey, you might be able to do this one component of design. I can support this tool, and it'll save you, 75% of the money that you pay for a license, and it's just as good. And I think there's a trade-off point there where some companies might start bringing in, open source tools again and doing their own development of tools like they used to do. It's maybe speculation, but like the noise tool you mentioned, Christoph. Yeah, that's a very specialized thing. But if you have a designer that's doing the noise analysis and they've played around with the open source stuff on their PhD thesis, they might say, hey, I know this tool, I can do it myself, and I'll support the tool for this company. That's just convincing management that, it's worth taking the risk and supporting a tool internally, which is what they got rid of, 20 years ago or so.
Yeah.
Okay. Yeah. Thank you both for your answers. So I will go with the questions from the audience. The first one is the open source PDKs also propelled a lot of learning opportunities for people to implement their own IC, EDA, CAD tools. Will this lead big companies like Cadence, Synopsys, Siemens to lose market on this field?
that's speculation. could happen, of course. I don't see this on the short run, to be honest, and I'd rather focus on the opportunities and not on where you lose something. I believe that the world is changing, and if I think back, about 10, 15 years when RISC-V came up the first time, nobody would have believed that today this is such a big success that a lot of companies now bet on this new open source based processor core. And yeah, the world is changing, and I believe it's better to adapt or be prepared for these changes than be scared of them, and rather look for opportunities that you can take.
Yeah, I would say I don't think those companies are going to lose market share, because I think they're smart and they're looking down the path and they're finding ways to differentiate themselves. They're providing features that the open source tools don't. A lot of these have to deal with the most recent technology nodes, which, as we know from an open source side, you don't even have access to them. And so you can't consider those effects, physics effects and things like that. So I think there's always going to be a market for that on the EDA, commercial EDA side. And I think it's a little bit of a false dichotomy where it's not either or. It should be open source or it should be proprietary tools. They can coexist because they have different markets and they address different needs.
Yeah, thank you for your inputs. And our next question from audience is, what effect do you believe open source IC design will have on lowering or rising the entry barrier for countries where IC design is not a predominant industry?
I believe this will help a lot. So I mentioned this Mosaic framework that we put together, 22. We've had people from university in Chile, Santiago, Chile. We've had people from the Philippines, and that's exactly what is meant by this democratizing IC design. So this is what we clearly see already today, that going open source will lower the barrier for people worldwide that can start doing hands-on IC design, and this was clearly not possible before.
Yeah, I agree with this. I think, I'm American, I'm from the US, and I think even inside our own country, we have such a disparity among schools and states that I think this even opens up opportunities within our own country to have students that have access that they didn't have before. And, I think in the US, we have a couple, maybe a dozen schools that are really highly renowned in chip design, and then maybe a couple dozen that have it. And I think this is going to open it up so that you can have hundreds or thousands of schools within our country. And so that same idea of what applies internationally is important here. And I think, we have a lot of federal programs that are looking to address this. And I think open source is an encouraging way to do that.
Right, thank you. Our next question is, you suggested that there are successful open source companies like Red Hat. An open source company must monetize to be successful. So what does an open source silicon business model look like? And is there any license issues?
Maybe I'll start with that one. I mean, licenses are always an issue. I think that the open source silicon business models, I think, are going to have to differentiate from the high performance, high end processor companies. And I think there's a market for having specialized niche products that are not such high volume, which is why I think it's actually not necessarily a disadvantage that open source stuff is on older technology nodes, because I think a lot of those products would want to be on lower cost, older nodes, but still get some performance of having dedicated hardware. So I think that there is a model, and I think basically to summarize it in a nutshell, reduce the barrier and make it easier for people to make a custom chip. And I think that's going to have a market in its own. And I think that's how they're going to have to do it.
Yeah, so I have no strong opinion here whether there's a market in licensing chip IP, for example. I could imagine yes, especially in differentiating IPs, but this will then not be open source but proprietary. So I see more opportunities in the ecosystem where companies can provide value, which is then created around an open source design system, for example. Like it's happening with RISC-V for WordPress.
Yeah. Thank you. Next question is, what is the role of machine learning AI for open source EDA, especially on analog design? And what are some of the successful stories of these approaches?
It's a good question. I would also like to have an answer on that. I gonna try one. So problem if you want to apply machine learning on analog design today is that there is not a lot of data out there. So that's different for many other things, which paved the way for the success of machine learning in other aspects. In analog, it's different. Even within our own company, we do not really have access to all our analog designs. And if we had, I mean, we would have, I don't know, 100 op-amps and not 10,000 that would be needed to do a meaningful learning. So we have to find other ways. And here, I believe open source can open a new opportunities by combined with analog generators. Think about, you could create, if you have analog, assuming you have analog generators ready, you can create your circuits and in different configurations, and then you create 1,000 or 10,000 different versions of an op-amp, and then you apply machine learning on it. This opens up new opportunities, and people are doing research on this. I cannot give you a good success story today, so there's not much publication out there on this, but it's an interesting topic for research, I would say.
Yeah, I'd agree that I don't think there's any success stories yet. I think we're really on the early stages of this. I think it's important to remember that, so I'm a strong believer in machine learning AI, but I think that it's important to remember that it's just a tool in your toolbox to solve problems. In a lot of cases, if you don't have access to data, let me take that back. If you know a problem and you understand the causes, you'll be better off making a customized algorithm to address that, and it will be better than machine learning. The area where machine learning does well is when you don't really understand the full problem, and it can fit data to come up with solutions that you wouldn't think about. So I think I always have an analogy of it's a toolbox, and you have like direct solvers and machine learning and all of these things provide solutions for different problems. So I think there are things that it can help. If you have a lot of data, you can fit that data to machine learning. You can also do unsupervised learning without data to come up with a solution. But you'll often find that you can come up with a better solution in a more direct way still. So it depends on the problem, is what it boils down to.
Right. Yeah. So our next question is, to maintain a healthy open source community, there needs to be a mechanism to provide regular updates and synchronize changes. Do you think there should also be some regulations around this, and how to achieve this?
So I believe not. I mean, the open source community has its own rules that were developed over the last decades, and if there's value behind what this community is doing with respect to a certain aspect, then there is no need for regulation. The regulation is done out of the community. That's at least what I've observed. So here I'm not a fan of regulation. What can help is, of course, coordination, like the foundations I mentioned before. They can help to steer the activities in a certain direction that all participants agreed before that it makes sense to go this way. But I don't think regulation is a good way to do it. It's somehow contradicting to the idea of open source.
Yeah, I agree. I think I would use a word of there should be an open source ethos, kind of something that we all believe. Because I think there's a couple tendencies. If there's an open source project and you want to add a feature, what a lot of people do is they'll fork the project, add their feature, and never put it back in the the main project. I think that's one of the worst things that can happen in open source design, because first of all, the thing never gets added back, so you don't gain from the community support. But also putting that back is part of the hard part. Like getting it upstreamed is a challenge. I think so. Forking projects and not contributing to the main projects is something we should all try to avoid, unless you disagree with the maintainer fundamentally for some reason. The other thing is consolidation. There's a lot of people that start different projects just because it's kind of encouraging when you start a project because you make so much progress. But once you get like 80% of the way there, the last 20% takes all the effort. And so that, it's exciting to start something new, but it doesn't really, you then end up having 5 different projects that are 80% done when you'd be better off having everyone work together and have one project that's 95% done. So I think there's a value for combining efforts that way as well. And that just has to be an ethos. That can't be regulated in any way.
Yeah. Thank you for that. And the next question is, what challenges do you see in building a trusted open source community where chip design companies, EDA companies, and university provide their unique contributions?
That's a hard question. I think, how do you get trust? I think you get trust through results, right? And track record. So I think it's not something we can kind of push towards. I think it just has to happen naturally in a way. I think people are going to start using more and more open source things and seeing how they succeed, and they'll gain trust. There will be some people that get bit too. They make a bad decision, an open source project is not verified in some way, and then they learn a bad lesson. So it's hard to answer.
Yeah, tricky question. Yeah, building trust is something that is not easy or straightforward. Yeah, and getting all parties in one boat is even more tricky. So you have to start somewhere and then go step by step, and yes, show results. And by showing the value and the benefit of what you're doing, building up trust step by step.
Yeah, thank you for that. And the next question is for the open source multi-project wafer. Usually it requires the designer to disclose their design for joining the shuttle. May you explain how that works and how we can protect our IP design?
Yeah, I think that one, so Google put a lot of money into those shuttles to kind of instigate open source design and the open source tools. And I think what they were looking for is to stimulate the field. And I think by definition, if you put a design on there that's proprietary, you're not helping the community. And so it was basically a requirement that you give back in some way. And so I think it makes a lot of sense that they were trying to bootstrap something. And so if you want to keep something proprietary, you can't have their money, right? That's basically the way they viewed it.
Yeah, right. And on top of that, I mean, I'm not directly involved here or cannot speak for the companies offering the open PDKs, but I would assume that there is a way, if not today, but then sooner or later, that you can do proprietary chips on these open source PDKs in their foundries. I mean, this is a viable business model should be behind this one. like Matthew said, now the initial work and also the PICO program, it's financed by other money, and they define the rules. But it doesn't say that in future there will not be other ways to do. I'm sure there will be other ways, because yes, of course, companies should be able then to design their own proprietary chips using these open source PDKs.
Right, thank you. So next question is, what are the challenges in verifying the correctness of open source IC design?
I would say challenge is, yeah, that you cannot be so sure about the tool quality. So there's always a bit of question mark if you use an open source tool chain. Again, it's a bit a matter of trust or of the community behind. I would assume in digital, the tools are more mature than in analog. And yeah, for example, back annotated layout results or RF simulations haven't been so well covered by open source tools until recently. And that's a challenge then, of course, if you tape out something in RF that you are not sure that's not 100% verified. 100%. It's not verified on a quality level that you would like to have it.
Yeah, I think part of this problem goes away. I know, I think it's a favorite quote from Tim Menzel from Google that basically if you have enough users, the verification problem takes care of itself. And so that's one of the things that he likes to cite. And I've always been a skeptic, but I actually kind of do agree with it somewhat, that if you have more users, people have tried to use it in more ways and will iron out more problems. So I think that's one of the metrics, is to increase usage.
Yeah. Okay, so there's I have the time for the last question. Is the open source PDKs only work for the specific foundry and process? Is there a risk that the foundry may not support scaling to latest processor nodes?
It's not a risk, it's a fact. So they offer what they offer, and that's it. And maybe they will open up other more technology nodes in future, or I'm quite sure they will do. There are plans for 90 nanometers and 65 and maybe 28, and I don't know, FinFET will come as well. But this will take some time, of course. There will always be a lag between the open source PDKs and the closed ones.
Yeah, I think there needs to be some change a little bit in the more advanced processor nodes, where they should have kind of a semi-open PDK. You know, like when you have cell libraries without the whole detailed layout and things like that. I think there's more opportunity for that, and some of the fabs should think about that, where they don't have to disclose everything, but they can disclose more than they currently do. And I think they have to decide where that line is, and that might help open source design a little bit more.
All right. Thank you. And I think that's all of our questions. And I would like to thank both of you, Christoph and Matthew, for your valuable inputs and your presentation about this topic. And this webinar will be available soon at the SCCS YouTube channel. So if you missed it, you can also watch that again. So I think that concludes the webinar for today. And thanks you, everyone.
Everybody.
Thanks,
Thank
everyone.
you.
Bye.
Bye.
Have a good day. Bye-bye.